Okay, so first of all, what we're going to do is we're going to go ahead and read this paragraph up here at the top. It's going to kind of explain concavity in a nutshell, and then we'll talk about some little things that you can use to kind of indicate, okay, when something is concave up or concave down. So first of all, you have already seen that locating the intervals in which a function f increases or decreases helps to describe its graph. In this section, you will see how locating the intervals in which the first derivative increases or decreases can be used to determine where the graph of f is curving upward or curving downward. So first of all, the definition of concavity. Let f be differentiable on an open interval. So once again, no sharp turns, no breaks in the graph. The graph of f is concave upward if the first derivative is increasing, and concave downward if the first derivative is decreasing. So now instead of dealing with the first derivative, you're now going to the second derivative. Now, the best way I like to liken concave up and concave down. Concave up would be something that would hold water. Okay, so if I were to pour water in here, that's something that could probably have a pool of water in it. Concave down, on the other hand, if you were to try pouring water, it's not going to hold water. It's going to spill over. Okay, so concave downward is something that is curved so that it could not hold water. Concave upward is curved so that it could hold some sort of water. Now, it could be a very little bit, okay, but still as long as it could hold a little bit of water, that could be kind of a way that you could visualize. So let's go ahead and look up here at this graph. Okay, I want you to just visually tell me, okay, what would the first graph, what does it look like it would be? Concave down. Now, actually, believe it or not, this one, if I were to extend it, actually has both. It has both, you're right. And we actually would break it right here. And if I break it here, what would the left part of the graph be? Down, because that's the water's going to spill out. What about the right side here? Up. Okay. What about down here? Up, because it's going to hold water. And now it's actually going to be upward on the entire interval. So now we're going to look at how you can do that algebraically, not only just looking at it. And so first of all, we have some tests for concavity. And once again, you have these on your sheet so you can follow along. First of all, let f be a function whose second derivative exists. If the second derivative is greater than 0, so in other words, what does that mean it is? Positive. So if the second derivative is positive, the graph is concave up. If the second derivative is negative, the graph is concave down. So it's kind of like the increasing decreasing thing. Okay? And now we're going to talk about points of inflection. Okay? Remember with an increasing decreasing, we have mins and maxes. With concavity, you don't have a min and a max. You have what's called a point of inflection. There's no two separate ones either. It's a point of inflection if the concavity changes, and that's it. So if your concavity changes from like concave up to concave down, you've got a point of inflection. If it's concave down to concave up, it's a point of inflection. Okay. Yeah. So basically, the theorem 3.8 states if CF of C is a point of inflection, then either the second derivative equals 0 or the second derivative does not exist, so it would be undefined. So we're going to go through the process for how you can test for concavity and how you can find points of inflection. And it's fairly easy. So find the intervals of concavity and locate all inflection points. So the first thing we got to do is find the first derivative, which you all should be able to zip off that nothing flat. What is the first derivative? Minus what? 3x. So then now we would use the first derivative if we were going to do increasing and decreasing. We're not doing increasing and decreasing. We're doing concavity, so I need to find the second derivative. And then we're going to go through all the same steps. So the second derivative, f double prime of x, is going to equal 6x minus 3. So if you remember what I just said, I said we're going to do all the same steps. So now we're going to set that second derivative equal to 0. And we don't call these critical numbers, we just call these possible points of inflection. So if I set that equal to 0, what value of x do you get? 1/2. So basically I would add 3. I would get 3 to equal 6x. So x equals 1/2. So this 1/2 is going to determine what your test intervals are. Okay? So I'm going to go ahead and do my negative infinity to 1/2. And then I'm going to do my 1/2. to infinity. You're going to pick a value in each of those intervals. What would be a value in the first interval? Let's pick 0. Okay, what would be a value over here? 1. So now, if you remember the increase and decrease when we plug it back into the first derivative, we're actually going to plug this back into the second derivative. Okay, so if I plug 0 back in here, I'm going to get negative. If I plug 1 in here, I'm going to get a what? Positive. So we can conclude that the graph is
It's upward.
concave. This one will be what? This will be concave down. This will be concave up.
Yeah, but it goes up. If you draw it out,
Oh, we don't worry about, no, don't worry about that, okay? So concave down, okay, I see what you're saying. The graph will be concave down from negative infinity to 1/2. And the graph will be concave up from 1/2 to infinity. The reason why we don't draw this up is because this actually is describing the first derivative. If a graph is concave down, remember it's going to look something like this. And if the graph is concave up, it's going to look something like this. Okay. And so now we need to conclude, do I have any inflection points? And the answer is yes, because your concavity changes. So we have an inflection point, or an IP, at 1/2. And then I need to find what coordinate that goes with. So where do you plug that into? The first equation, right? So I'm going to plug it in up here. So I got 1/2 cubed minus 3/2 times 1/2 squared. So I get 1/2 cubed to be 1/8 minus, what's that, 3/8? So what's it come out to be? Negative 1/4? Somebody get negative 1/4? Okay. So there you go. That's it. That's concavity. We're going to look at one more, and then that will be all we'll cover today. And then tomorrow, Monday, we'll talk about the second derivative test. We'll continue with this section. All right, so let's go ahead and look at this one. F of x equals x to the 4th minus 4x cubed. What do you do first? Yep. So what's the first derivative? Okay. What do you get for the second? Okay. 12x squared minus 24x. So set it equal to 0. Good. Take a 12x out, and that leaves you with what? X minus 2. So you have two possibilities. What are those possibilities going to be? 0 and 2. Did you get it? Okay. So I go negative infinity to where? 0 to where? And? To infinity. So I have negative 1. Yep. 3. Where do I plug those numbers in? Second derivative. So if I plug those in here to the aqua color, I get a negative times a negative. So net result will be a positive. Well, I mean, it would be like we did second derivative. I mean, it's the same thing. So if I plug it into 1, what do I get here? Positive, negative. What's a positive times a negative? Negative. Plug in the 3, what do you get? Positive, positive. Now, if you don't like doing the positive negative test, that's fine. You can actually plug that value in and get a number. Okay, so you could get like 36 times 1 for the 3, and that would be fine. So what can you conclude? Yep. Okay. So I know it's concave up in two locations, from negative infinity to 0, and from 2 to infinity. Oops. Try that net infinity sign again. And it's concave down from 0 to 2. I got two inflection points. Oops. Where's the two inflection points going to be at? 0 something and 2 something. 0, 0? Yep. And 2 what? Negative 16. Good. So there you go. So now you're not going to be able to do your entire assignment. Okay, you'll be able to do some of them. But let's go ahead and start by looking at 1 through 8. I think that's what you have. Okay, 1 through 8 is going to be one of those that you're going to use your visual views there. So if I look at number 1, they want you to just visually look at that and determine is the graph concave up or concave down, and if it is, where and what. Okay. So number 1 is pretty easy. You can see that that's going to be what? Concave up from where to where? Negative infinity to positive infinity. Now number 2. It's concave up and concave down. Now the question is, where exactly does that break? So what you need to do, and this is the key, if you have something like this, and you need to determine where it's concave up and concave down. Now this is something you might want to pay attention to. Okay? If you have something like this, all right, you're going to break that right here. And so the left of that green will be your concave up, and the right of that green will be your concave down. So in that specific one, what x value will that break at? 1. 1. There you go. Okay. Alrighty. So once again, we'll continue Monday.